All right, guys, today, fundamental theorem of calculus. So we're taking these ideas that we've been studying, indefinite integration, Riemann sums, the exact area under a curve, and we're kind of linking them all together and combining them into what's known as the fundamental theorem of calculus. So what this theorem says is that if the function f is continuous from a to b, and capital F is an antiderivative of little f from a to b. So we've got to be careful with these notations. So basically it's saying that capital F is the original function because it's an antiderivative. So it's the original function. Little f is big F prime in this case, okay? Little f is the derivative of big F. And I don't know why this is presented in so many different ways, but it is. Sometimes on the test, big F is going to represent one thing, and others it's going to represent something different. So in this case, big F is our original function. Little f is the derivative of big F, okay? So it's saying that if I take the integral from a to b, so I'm not taking an integral from negative infinity to infinity. I'm taking a definite integral from a to b of f of x dx. Then my answer, rather than having to find the area under the curve and go through all this work, if I just take the antiderivative, if I just integrate f of x, then my answer becomes my integrated function f from b minus f of a. So all I have to do is integrate f of x, and then I plug in b, and I plug in a, and I subtract them. Okay. So for example, we are going from negative 3 to 2 of 2x dx. Negative 3 to 2 of 2x dx. So when I integrate that, I'm looking at 2x, and x has to go up to 2, which means I'm going to have to put a 1/2 in front. And I already have a 2 in front. And then don't forget that we end up with a plus c, right? So this becomes 2 times 1/2 is just 1. So I end up with x squared plus c. But this isn't an indefinite integral. This is a definite integral going from negative 3 to 2. So the way I write my notation here is I am going from negative 3 to 2. So I take x, instead of x squared, I plug in the 2. 2 squared plus c minus, and then I plug in the 3. Negative 3 squared plus c. So I end up with 4 plus c. Negative 3 squared is 9. This negative distributes to make it a negative 9. This negative distributes to make that c a minus c, which is nice because when we're doing definite integrals, when we're using this theorem, those c's, they still cancel out. So I end up with 4 minus 9, I end up with negative 5 is my answer. So instead of having to graph this and find the area, I just take the integral and I evaluate it at 2 and evaluate it at negative 3 and subtract. So my answer would be negative 5. Now I can check this on my calculator. Guys, if you go to, let's get out of this window and let's just go back. So if I hit math and then I hit 9, if you notice down here, it's asking for an integral. Now this only works when we're doing definite integrals, when we know what our endpoints are. So I'm integrating from negative 3 to 2, and my function is 2x. When I hit enter, it tells me my answer is negative 5. Okay? We could also check this on the graph. If I go up here and I put in 2x to my graph and look at the picture, remember I can do second calculate, and number 7 down there looks like an integral. So I hit 7, and it wants to know my left bound, so I'm going to put negative 3 as my left bound. My right bound is going to be 2. And it tells me down here at the bottom, f of x dx equals negative 5 when I'm going from negative 3 to 2. So -5 seems like the right answer. Now on the AP test, you're going to have to do this by hand. And you're not going to be able to rely on just getting the answer on your calculator. If you're able to use your calculator, go for it. Get that answer really quick and move on to another problem. But you are going to have to do this by hand on the AP test. So just make sure that you can do it both ways. The calculator really is going to be a strong tool to help make sure, especially on the homework, that you're doing it correctly. Whether it's a calculator question or not, you can always check your answer with the calculator on the homework. All right, so let's do a couple. 0 to pi fourths, of 4x plus secant squared x dx. So the fundamental theorem tells me that if I take the integral of this function, if I integrate it, and then I just have to plug in 0 and plug in pi fourths and subtract and see what I get. So I'm going to start by integrating the 4x. So the x is going to go up to an x squared. I already have a 4 in front, but because it's going up to an x squared, don't forget I have to multiply by that half. Now, I'm not going to write a plus c because I don't have to write a plus c. Remember, when we're doing definite integrals, when there's points here that we're integrating between, that c just cancels out. So 1/2 4x squared. Secant squared x, if we've been practicing our trig derivatives, secant squared is the derivative of tangent of x. If I take the derivative of tangent, I get secant squared. So going backwards, secant squared goes backwards to be tangent of x. Now I have to evaluate this. Well, let's simplify first. 1/2 times 4, that's 2x squared plus the tangent of x. And I'm going to evaluate this from 0 to pi fourths. So I plug in the bigger number first, the pi fourths. So 2 times pi fourths squared plus the tangent of pi fourths. And then I'm going to minus 2 times 0 squared plus the tangent of 0. Not too bad so far. So as I start to simplify this, 2 times 0 squared, that's just 0. My tangent at 0, remember we're looking at tangent is sine over cosine. And so my sine at 0 degrees over my cosine, it does exist because my sine is 0 and my cosine is 1. So 0 over 1 is 0, so tangent of 0 is 0, so that all just cancels out. Which means on this side, I end up with, what, pi squared on top. 4 squared on the bottom is 16, but I've got this 2 on the top. Well, let's just write it so we can follow the algebra. So 2 pi squared over 16 plus the tangent of pi fourths. So if I do the sine over the cosine at pi fourths, we get 1 because they're the same thing. And then 2 over 16 simplifies. This becomes pi squared over 8 plus 1. And that right there, that's a good answer. I don't need to get an exact not an exact decimal. I don't need to take this exact number and turn it into a great big ugly decimal. I'm okay with this answer right here. If I wanted to check my work again, we could put this into the calculator. I can go back here. Let's do it the y equals way, just because I think these functions look cool sometimes. So I'm going to put in my original function, 4x plus, now secant squared x. I don't have secant, but remember, secant is what? 1 over the sine squared. Oops, let's do sine. Where are we? Sine x squared. That looks right. And then when I graph it, now because I calculated the integral before, it's still there. If I hit clear, that'll go away. So here's my graph. I'm going to set my limits, though. I'm going to set my lower limit to 0 Nope, 0. I'm going to set my maximum. Let's do pi fourths, because that's what we're evaluating to. So if I look at this graph, maybe we need to change our... No, we're all right. So here's my graph. If I open this up a little bit, like if I make my x maximum, let's go a little bit bigger, I guess. We can go 25, so we can see a little bit more. If I wanted to evaluate this, if I do second calculate, and I want my integral 7 from 0, enter, and then I want to go, why is my input invalid? Left bound, 0, please. Why doesn't it like my left bound? 4x is my function, right? Plus secant squared. Oh, because secant is cosine, not sine. I need cosine of x squared. There we go. So now if we integrate, second calculate, integrate 0, enter, and then my right bound is my pi fourths. So second pi divided by 4, enter, enter. And I get what? If I look down here at the bottom, f of x dx is 2.23370. If we want to double check that, what did we have as our answer? Pi squared divided by 8 plus 1, 2.2337. So we've got the right answer. You can check it either way. Just make sure you know how to double check your work there. Okay, so going back to problems. Let's get rid of some of this. And let's look at this absolute value one. So absolute value graphs, I know, scare people sometimes. I think really, because it's just a V, sometimes drawing this graph, even though we've got a calculator and we can do this on a calculator, sometimes drawing the graph is a little bit easier. And one of the things I look for first when I look at this function right here is what makes my absolute value 0. Okay, what makes 4 minus 2x equals 0? Well, if x is equal to 2, then that's going to be 0. And what that tells me is that x equals 2 is that bottom point. It's that sharp point of my absolute value graph. And then from there, I can look to the left and to the right to kind of get my slope. So if I go to the left 2 and plug in 0, 4 minus 0 is just 4. So that means as I go to the left 2, I'm going to go up 4, which means as I go to the right 2, I'm also going to go up 4. Okay, so there's my graph with my super straight lines. Don't worry about it. So really what we're doing is, let's ignore that absolute value for just a minute. When I'm integrating, when I go from 0 to 2, I'm going to be positive, right? When I go from 0 to 2, the inside is going to be positive because 4 is going to be bigger than my minus 2x. So as I integrate from 0 to 2, I'm integrating 4 minus 2x. Well, and I guess we should put dx, right? But then, remember how we can break up these integrals? I can integrate from 2 to 5, but from 2 to 5, look at this line right here. It's not 4 minus 2x. It's negative 4 plus 2x dx. So my sign switches when I pass that curve. So even though from 0 to 2, this is my function, once I pass that sharp point, now my slope is the opposite way. and so I have to change my sign. So it becomes negative 4 plus 2x dx. Now doing this, the integration right here, we are more than welcome. You can just plug in, we can do the fundamental theorem of calculus. So I can take 4 minus 2x, and that becomes 4x minus the 2x becomes x squared, but I have to times by a half, and I still have that 2. And I'm going to evaluate that from 0 to 2. And then I'm going to add negative 4 becomes negative 4x. And my 2x squared becomes plus 1/2 2x, or my 2x becomes plus 1/2 2x squared. And I'm going to evaluate that from 2 to 5. So we can use the fundamental theorem of calculus here. Now I can plug in 0, or plug in 2 first, right? So I get 4 times 2. Negative 1/2 times 2 is just negative 1. So minus 2 squared. But then I have to minus plugging in 0 into everything, but that just all becomes 0. So I'm just going to put a minus. And then I'm going to add. Over here, I've got to plug the 2 in right there. So negative 4 times 2. And then I've got to plug the 2 in on this side. And again, that just becomes 2 squared. But then, don't forget that you are going to have to subtract. And I thought I left myself enough room. And I can't zoom out further than that. So I'm going to rewrite this down here just a little bit. 4 times 2 minus 2 squared minus 0 plus negative 4, 2 plus 2 squared. But then I've got a minus. I plug in the 5. So I've got a minus negative 4 times 5. And I've got to plug the 5 into the x squared. So that becomes plus 5 squared. So 4 times 2 is 8. Minus 2 squared, that becomes minus 4. The 0 goes away. Negative 4 times 2 is negative 8. 2 squared becomes 4. Negative 4 times 5 is 20. Negative 20. And a negative 20 is a positive 20. And then a negative 5 squared becomes negative 25. So those cancel, and I'm left with negative 5 again. Maybe. Let's check our work. So this, and of course I erased. Don't do that. Okay, so we think that our answer is negative 5. If this was me doing this problem, this is a great example of the fundamental theorem of calculus, but when I look at this shape, I've learned that I can find the area from here to here and the area from here to here, and I can add those together and get the same answer. I don't know about you, but that looks a lot easier to me because I know that really this is just a triangle that's 4 by 2, and this is a triangle that's 4 by 2. So if I take 4 times 2, cut it in half, what do I get? 4 times 2 is 8, divided by 2 is 4, plus another 4. So my area is 8. So somewhere, someone did some bad math calculations. Where did we forget? I'm sure we messed up our algebra somewhere. Or we made a mistake right here with the area. But the area looks pretty good to me. So I'm guessing it's down here in our algebra somewhere that we goofed up. And by we, I mean you, because this was totally your fault. I'm doing everything I'm supposed to do. There it is. When I plugged in my 2 and my 5, I plugged in my 2 in the front and the 5 in the back. It's the other way around. So this should have been 8 minus 4 minus 0. This part should have been positive. So that should have been a negative 20 plus 25. and this one should have been negative. So that negative 4 times 2, that negative 8 would have become a positive 8, and that 2 squared would have become a minus 4. So let's see what happens now. I've got 8 minus 4 is 4. 8 minus 4 is 4. Negative 20 plus 25 is 5. So 4, 4, and a 5. My algebra is still wrong in here somewhere. I'm assuming maybe our graph is a little bit wrong. Let's look at this really quick. Math, absolute value of 4 minus 2x. And when I graph it, let's do window, nope, zoom, standard. Let's calculate our integral. And we're going from what? 0 to 5, yeah? 0. Oh, maybe that's why. That's why. We're going to 5. We're not going to 4. So this answer right here is correct. 4 plus 4 plus 5 is 13. I'm going too fast. When I did the area right here, we're not going from 2 to 4. We're going over here to 5. So this triangle is what? 6 tall. So 6 times, and it's 3 wide divided by 2. So that's a 9. So this is 9, this is 4. So when you add those together, you get 13. There it is. So when you make a mistake doing the geometry and make a mistake doing the algebra, then you're really in trouble. Don't do either of those. But I think we've got that one cleared up. We can go over that one in class if we need to, because we kind of bounced around right there. We've just got to remember, when we integrate, you take the top and you minus the bottom. Don't do it the other way around, or you get the wrong answer. Okay, so looking at a calculus test, an AP test question. We've got a lot going on here. We're not going to do the entire thing. Let f be a function defined from -3 to 4. So we know it's a function. It's defined. It's a closed interval. And it tells us that f of 0 is equal to 3. And it gives us the graph of the derivative. So this is f prime that it gives us the graph of. Now, we're not going to worry about A, B, and C. We're going to just focus on D today. It wants us to find f of -3, and it wants us to find f of 4. Now, I think this is kind of a cool question because it takes a lot of what we've done and combines it all together. So if I look at, I have no idea what f is. I know what the slope at -3 is, but I don't know what the value of f of -3 is. And not only that, but if I look at my function, this is not a nice, simple function. This looks like a really messy piecewise function, right? So I do know that if I take the integral of the derivative, so let's say I go from -3. Now, I don't want to go from -3 all the way to 4. I'm going to stop right here at 0. I'm going to split this up into 2 different problems. So I'm going to go from -3 to 0, and I want to integrate f of x. So my answer is going to become the derivative. It's going to become, well, I guess I want to integrate f prime of x, right? So my answer becomes regular f of x because f of x was the original function, but I have to evaluate that from 0 to -3. Actually, -3 is our bigger one. So we better put it on bottom, or we better put 0 is our bigger one, -3 to 0. So what that means is I've got to go f of 0 minus f of -3. Well, I know f of 0. It tells me up here f of 0 is 3. So this is 3 minus f of -3. And now I get to use my graph a little bit because I don't know I don't know what f of negative 3 is, but I do know that if I use the area, if I look at my graph up here, I can find the area of these pieces, and I can use that information. I've got a triangle right here, and it's 1 wide, and it's 1 tall. So I've got this little 1 by 1 triangle, which means the area is 1/2. Then I've got this triangle that is 2 wide and 2 tall, so it's a 2 by 2. And that makes the area of the inside 2. But I've got to be careful because this area is above the curve, this area is below. So the 1/2 is positive, but the 2 is negative. So if I add these two areas together, I get negative 3/2 or negative 1.5. And if I come back down here, I don't know what f of negative 3 is, but I know that when I combine these together, I should get negative 1.5. So if I minus 3, if I do my old railroad tracks thing here, minus 3, negative 4.5 equals negative f of negative 3. Don't forget that negative sign right there. So to get rid of that negative, this becomes a positive, this becomes a positive. So f of negative 3 is equal to 4.5. Now that was a lot to follow. So let's do the same thing for this, for f of 4. Okay, so f of 4, I know that the integral from 0 to 4 of f prime of x equals f of x evaluated from 0 to 4, which equals f of 4 minus f of 0. And again, I know f of 0. F of 4 minus f of 0 is 3. But I don't know this side of the equal sign. I do, right? I can use the area because this is the integral. I'm finding the integral, and I know that the other way I can find the integral is to find the area under the curve. Now, this one's a little bit messier because it's not just a nice, I don't have just nice triangles. I'm actually looking for this area right here and this area right here put together. I'm not looking for the inside of the semicircle. So I'm actually going to take the rectangle and I'm going to subtract my semicircle. See this big rectangle right here? That big rectangle is what? It's 4 wide and it's 2 tall, so that's 8. My big rectangle is 8. My semicircle, it's a circle with a radius of 2. So my semicircle is pi r squared, right? But it's pi r squared, but I have to divide it by 2 because it's a semicircle. So my area of my semicircle just becomes 2 pi. Right? Because this is pi r squared, which is pi 2 squared, which is pi times 4, but it's a semicircle, so I divide by 2. So that's where I got my 2 pi. So I've got 8 minus 2 pi. So I can come back down here and say, all right, so 8 minus 2 pi is equal to f of 4 minus 3. So if I add 3 to both sides, 11 minus 2 pi equals f of 4. And I'm okay with that answer. That looks like a good one to me. No, it doesn't. Because this area is negative. We're under the curve. So that 8 minus 2 pi, we need to come back down here. Come on, eraser. Help me out here. That 8 minus 2 pi is actually negative 8 plus 2 pi because my area is under the curve, so it's a negative. So I have to change the sign. So now when I minus 3, I add 3 to both sides, and this becomes negative 5 plus 2 pi equals f of 4. That looks a lot better. And again, this one we're not going to really be able to check our work because we don't know what the original function is. So we're going to have to trust our algebra, which might be a little bit scary because we've done some goofy things today. All right, definite integrals that are ugly. Now, this is a really cool trick that we use a lot just to save you on some time. But when I look at this integral of x times x squared plus 2 squared, if this wasn't here, if it had just said the integral of x times x squared plus 2 squared dx, you would use, hopefully your first thought would be u substitution. And nothing's changed. We still want to use u substitution. We don't have to. You could FOIL that out. You could distribute the x, and then you could just do it the normal way. But that's a lot of work, especially when I can just say, look, let's let u equal x squared plus 2. That means that du is going to equal 2x dx, which means that 1/2 du is going to equal x dx. If you need to pause and follow that algebra, go ahead. So I've got my u, I've got my 1/2 du x dx that's going to replace everything. So I've got the integral, but instead of the x and the dx, that becomes my 1/2 du. And I'm going to plug in u right here and get u squared. But there's one other thing we need to take into consideration, and that's these limits right here. Now, if I leave them the way that they are, after I integrate, I have to take all of this stuff, this x squared plus 2, and I have to plug it back in. Or I can take my limits and I can plug them in and get new limits. So if I plug in a 0 to my u function, u equals 0 squared plus 2, which is just 2. And if I plug in a 2, u equals 2 squared, that's 4 plus 2, that becomes 6. So my new integral is 1/2, 2 to 6, I just moved that 1/2 in front, u squared du. Now I do what I've always done, right? I'm going to make this u to the third, which means I have to put a 1/3 out in front, and I already have a 1/2 out in front. But this time I need to go from 2 to 6. Instead of going from 0 to 2, I'm going to leave the u a u, and I'm going to go from 2 to 6. Let's see. We'll put the 1/2 in right now. Let's make this 1/6 u cubed from 2 to 6. So that becomes 1/6 6 cubed minus 1/6 2 cubed. So that becomes what? Well, this 6 cancels one of these 6's, so it becomes 6 squared, which is 36 minus. 2 cubed is 8. 8 over 6 becomes 4 over 3. So 36 minus 4/3, that's a great answer. But if it was, if this was something that, like on a multiple choice, it might want you to actually multiply this by 3, which is what? 108 minus 4/3, so 104/3 is also an acceptable answer. Either way, we can check our work. If I go to my calculator, and we'll do this in the normal window this time. I'm going to go math 9, and I'm going from 0 to 2, and I'm going to put in x parenthesis x squared plus 2, close parenthesis, and square that. Enter. So 34.666667. So if I take my 104 over 3, What do I get? 34.6666667. We get the same answer. Okay, it's a really powerful theorem. It lets you do a lot of things. I like these examples right here, which we didn't go over the scoring guidelines. We can talk about that in class. On part D right here, you would have gotten 1 point for using the areas of these triangles and finding that area was 1.5. You would have gotten 1 point for getting our f of 3 answer. Where did our f of 3 answer go? Right here. This would have gotten you a point, and you would have gotten 1 point for the f of 4 answer. Oh, and you would have gotten another point for, let's see, where'd it go? Where's our work? Right here. You would have gotten a point for doing the rectangle minus the semicircle. So on this one, you got 4 points for part D. You got a point for doing this rectangle minus the semicircle. You got a point for doing the triangle plus the other triangle, or the difference between them, I guess, because the bottom one's a negative. If you did that correctly, you got a point for each, and then you got a point for the answers. We can cover those more in detail in class, and we'll do some more examples as well.